Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin a new topic called Application of Derivatives. Now, we've studied basic differentiation in 11th class, and now we've seen it again as it relates to continuity and differentiability. So let's see what the differential really means. If we have a function y of x is equal to x squared, then we have dy by dx is 2x, right? So what does dy by dx really mean? Well, you can look at it from two different points of view. Either you can take the algebraic point of view, which states that dy by dx is the rate of change of y with respect to x. So dx will be a small change in x. As x changes from a value x1 to say a value x2, y will change from a value y1 to a value y2. So dy will be the small change in y. Since it is a finite function, a very small change in x has to necessarily give a very small change in y. And dy by dx will be the ratio, will be 2x, which is the rate of change of y with respect to x. Another thing that dy by dx can mean is the slope of the graph of y of x, right? We saw this from a very basic perspective in 11th class. If you have a curve, then at any point dy by dx denotes the slope of the tangent, tan theta, right? We'll get back to it in the next video where we'll see more applications of derivatives such as tangents and normal, but this geometric point of view we'll leave for now. Right now we'll focus on the algebraic point of view that says that the derivative of y with respect to x is the rate of change of y with respect to x. We've already seen examples of this before in 11th class physics, where we noted that if x is a function of time, let's say t cube plus 3t, v will be dx by dt, which is the rate of change of position. If you look at the rate of change of y with respect to x, here is x with respect to t, and x is the position. So rate of change of position with respect to time. Now in physics, when we say the rate of change, we generally mean with respect to time. The rate of change is generally used for with respect to time, but in mathematics the rate of change can be anything, because we don't talk of time in mathematics, we just talk of variables y and x, right? We also saw acceleration was the rate of change of velocity, dv by dt, right? And you can look at some other examples as well. Let's say we have a circle of radius r, and r is changing. Let's say r is a function of time, and it is equal to 3t squared, which means this circle at t is equal to 0 seconds has no radius, at t is equal to 1 second has a radius of 3 units, at t is equal to 2 seconds has a radius of 12 units, and so on. Right. So first of all, we can calculate dr by dt. It's of no real use here because it's just the rate of change of the radius. It is 60. Right. But what will change if the radius changes? The area of this circle will change. The area of this circle is given as 2 pi r squared. Right. And as the radius changes, the area will change as well. So we can calculate the rate of change of area with respect to time. Let's just look at it with respect to radius first, and we'll use the chain rule. So the rate of change of area with respect to the radius will be dA by dr. And that you can see from here, the derivative of r square is 2r. So that will be, I'm sorry, I don't know why I wrote 2 pi r square here. The area is obviously for a circle is pi r square. So my apologies. So area is pi r squared, dA by dr will be 2 pi r. The rate of change of area with respect to the radius is 2 pi r. And that sort of makes sense, because if we increase the radius by a small amount, let's say, then what is the change of area? It does seem to be this area, because if the radius changes by a small value, then the circle's area increases. This ring seems to be the change in area. What is the area of this ring? That is 2 pi r multiplied by dr. 2 pi r is the circumference, dr is the thickness. So 2 pi r multiplied by dr is this small area. So we can see dA is equal to 2 pi r dr. However, we can also calculate the rate of change of area with respect to time. So before this, whatever we've seen, A is equal to pi r square, dA by dr is 2 pi r, dA, which is the small change in area, will be the circumference multiplied by the change in radius. That is valid for any circle. Now we look at the specific circle in which the radius is changing such that r is equal to 3t square. In that case, dr by dt is equal to 60. What we need is dA by dt, the rate of change of area. That can be written as dA by dr into dr by dt. We are using chain rule here. Dr will cancel, it will give me dA by dt back. But we know these two quantities separately. dA by dr from this equation is 2 pi r, and dr by dt from the above equation is 60. And we can substitute r is equal to 3t square here as well. So what we'll get is, this will be 3t square, so we will get 36 pi t squared. So this is the rate of change of area. That means at t is equal to 1 second, the area is changing at a rate of 36 pi units. If we are talking about meters, then 36 pi meters square per second. So the rate of change of area you can calculate as the rate of change of area with respect to the radius, because you already know the formula for A as a function of r, multiplied by the rate of change of radius. Let's just look at another example. Let's say we have a cube of side L. That means the volume of the cube will be L cube, right? So if the side of the cube, the length of the cube is changing, that means the volume will change as well. Let's look at the surface area as well. What will be the surface area of the cube? It will be 6L squared, because you have 6 faces. Each face will have an area of L squared. We can calculate the change of both of them with respect to the length. So dV by dL will be 3L squared, and dA by dL will be 12L, right? And so this is all general. The small change in volume will be 3L square multiplied by the small change in length, and the small change in area will be 12L multiplied by the small change in length, right? Now let's say L is changing with respect to time such that L is equal to 5t plus sin t. Let's just add 2 as well, because we don't want L to be negative ever, right? So let's say this is the function for L of t. At t is equal to 0 seconds, L is equal to 2. At t is equal to 1 second, L is equal to 7 plus sine of 1. 1 will be in radian, obviously, right? So in this case, we can now calculate the rate of change of volume and area with respect to time as well. dL by dt, the rate of change of the length, will be 5 plus cos t, which means dV by dt, the rate of change of volume with respect to time, will be dV by dL multiplied by dL by dt, which we can see as 3L squared multiplied by 5 plus cos t. And you can put in the value of L if you want as well. 3 times 5 plus cos t times 5t plus sin t plus 2 whole square. Similarly, dA by dt, the rate of change of area, will be dA by dL times dL by dt. The chain rule is equal to 12L, which is 5t plus sin t plus 2, 12L multiplied by dL by dt, which is 5 plus cos t. So you can see the first application of derivatives, so to speak, which is, if you know the rate of change of one function, you can calculate the rate of change of another function if you know the relation between the two. From this comes another application of derivatives, which is an extension of this, which is making approximations for functions. So let's just start with a very simple example. Y is equal to 5x and dy by dx is equal to 5, right? And let's say we know that y of 10 is equal to 50. We want to calculate y of 10.1 and y of 10.5, let's say, and y of 11. Now obviously you can multiply by 5 and get the answer, but I'm just trying to show you how you could also use approximations, and then we'll see how to use approximations for more complicated functions. Right. So dy by dx is 5, which means the rate of change of y with respect to x is 5. So the rate of change of y with respect to x is 5. That means as x changes, y changes 5 times as fast. Right. So let's say we know that y of 10 is equal to 50. We want to calculate y of 10.1, which is y of 10 plus 0.1. Right. Now what we can do is we can write this as y of 10 plus something. And what is this something which we need to write here? So at x is equal to 10, the value of y is 50, right, which is y of 10. Now as x increases by an amount 0.1, so we have changed x by a small amount. As x changes, y changes 5 times as fast, right? So if x changes by 0.1, y will change by 5 times 0.1. Because that's the original meaning of dy by dx is equal to 5. The rate of change of y with respect to x is 5. Right. So we will say y of 10 plus 0.1 is simply y of 10 plus 5 times 0.1, which comes out to be 50 plus 0.5, which is 50.5. And because this is such a simple function, we already knew the value of 10.1, that had to be 50.5. Right. Let's just remove the second case because we just need to do the second one, the third one, to be able to understand it properly. What about y of 10 plus 1 or y of 11? That we can write as y of 10 plus 5 into 1, because we know the value of y of 10, that is 50. What happens when we increase x by 1? Y changes 5 times as fast as x, because the rate of change of y with respect to x is 5. So if x changes by 1, y changes by 5 times 1, which gives us 55, which is the answer we would expect. Right. Now, I only used approximations in this simple case to try to show you how it would work, but there's one interesting thing about this specific function. Dy by dx is a constant, right? It is 5. So it is always constant. It doesn't matter whether x is 10 or 10.1 or 11 or 50 or 100, dy by dx will always be 5. So these relations are quite valid. But now let's say we were talking about y is equal to, let's say, now we are talking about 5x squared by 2. In that case, dy by dx would be 5x. Right, so now we are talking about a completely new function, 5x squared by 2. The derivative of that would be 5x. So now dy by dx is 5x. That means it is increasing with a rate that depends on x. When x is 1, it is increasing 5 times as fast as x. When x is 2, y is increasing 10 times as fast as x. When x is 10, y is actually increasing 50 times as fast as x. Right. So the first case was a very special case in that dy by dx was a constant, but most cases will have dy by dx, the rate of change will be depending on x. Right. So let's just try to do a similar case. I won't do 5x squared by 2 because of the factor of 2. So let's just do 5x squared. Right. So let's say now y of x is equal to 5x squared. And we know the value of y of 10, which is 500. Right. And let's say we want the value of y of 10.1 and y of 11. Right. So what we can do is dy by dx is equal to 10x. Okay, if you were to calculate the exact value, this would come out to be 510.05 and this would come out to be 605. Right, you can put it and check. So dy by dx is 10x. That means dy by dx at x is equal to 10 is equal to 100. Right? So at x is equal to 10, we know what the rate is. It is 100. But what is it at x is equal to 11? It is 110. So dy by dx is changing. Right? Now if dy by dx was constant, let's say dy by dx was constant 100, then we could write y of 10.1 is equal to y of 10 plus 100 into 0.1, and we could write y of 10 plus 1 is equal to y of 10 plus 100 into 1. Right? The same way we wrote equations in the previous case, if dy by dx was a constant value 100, which would mean y is 100x. So if dy by dx was a constant value, then these two relations would be true. But now these two relations are not true because dy by dx is not constant. So even between 10 and 10.1, dy by dx is changing. It's going from 100 to 101. Between 10 and 11, dy by dx is certainly changing. It goes from 100 to 110. Right? So because dy by dx is changing, we cannot really use these two equations. Not correct for both of them. Because as we go from 10 to 10.001, dy by dx changes a little bit. It's not 100 anymore. We go from 10.001 to 10.002, it changes again. Right? So these equations are not correct. Now here is where the key part comes in, where we will try to approximate functions. We say that as long as the change in x is small, remember here the change in x is 0.1 and here the change in x is 1. We go from 10 to 11. So the approximation we make is, we say as long as the change in x is small, we'll assume that the rate does not change very much between that. So if we assume these two relations to be correct, just for a second, let's just humor me and assume these two relations are correct. In that case, what we are really assuming is dy by dx does not change from x is equal to 10 to x is equal to 10.1. If dy by dx was not changing between these two values, then this relation would be completely true. What we'll say is, we'll assume that the change is so small that the change in rate of change can be neglected, so to speak. So here dy by dx is 100, here dy by dx is 101. So we'll just assume it's 100 in both the cases because 100 and 101 are very close. Now in this case, 100 and 110 are not that close. So as long as delta x, the change in x is small, this approximation seems to be valid. But if delta x changes by a big amount, then this approximation is not really valid. So let's look at the actual values. 100 into 0.1 is 10. Y of 10 is 500. So this gives me a value 510. And this gives me a value 100 into 1 is 100 plus 500 will be 600. So the actual value is 510.05, but I get 510, which is quite close. We can say that this approximation is somewhat valid. But if we change x by a decent amount, we change x by 1, that means it goes from 10 to 11. Dy by dx changes quite significantly from 100 to 110, and so we don't get the correct answer 605. What we get is 600, and for some purposes you might say this approximation is too far off. We don't want it. We want it to be somewhat closer. Right? So this is the essence of approximation. As long as the change in x is small, even if x is changing, as long as the change is small, you can assume that the rate of change is constant. Now let's just put it into a little bit more formal definition. Right? Let's just say y is a function of x, and we are talking about 2 points. The first point is x and the second point is x plus delta x. Right? Now here I'd like to make a very important difference, the difference between delta x and dx. Dx is an infinitesimal quantity. dx is smaller than the smallest value you can ever imagine. It is smaller than 0.01, it is smaller than 10 to the power minus 100, it is smaller than the smallest value you can imagine. It's not even really a value, it's a placeholder for the smallest number possible without it being 0. Delta x is an actual value, so delta x can be 0.1 as it was in the previous case, it can be 0.01, it can be 0.45 or something. So delta x is a real number, right? We say x goes from x to x plus delta x, which makes y go from y to y plus delta y, right? And dy by dx we can obviously write as y dash of x. Now the claim we make is this: as long as delta x is small, delta y is equal to dy by dx times delta x. And this relation is quite important, but also this relation is why I wanted to make this difference. Dy is a very small number. In fact, the differential change, by the way, dy is called the differential change in y, dx is called the differential change in x. A differential change is actually basically 0. It has no value, it's smaller than the smallest value possible. It only makes sense when you have the ratio of two of them. So they both could be extremely small, yet could have a ratio between them, which would be finite. One could be 2 times the other or 5 times the other. So dy is very small, dx is very small, dy by dx makes sense. It's a function, it's a ratio. Delta x on the other hand is an actual change in x. When you go, like in the previous case, from x is equal to 10 to x is equal to 10.1, what we are saying is x is 10 and delta x is 0.1. But dy by dx was still, we took 5x squared, so it was still 10x, right? So dy by dx is a function. Dy by dx will be either dependent on x or not, but it's a proper function. Delta x is the small change in x, and this is the relation we say delta y is equal to dy by dx times delta x, as long as delta x is small. Let's look at one more application of this case. So we know root of 100 is 10. Let's say we wanted to calculate the root of 100.01. Now I'll just to make this clear, root 100.01, if we use this method, might actually give us quite a reasonable answer. But we tried to calculate the value of root 101 by this method. It would give us a much less accurate answer. And we tried to calculate the value of root 200 by this answer, by saying x is 100 and delta x is 100. Then we'll get a completely nonsensical answer, because even though the change of dy by dx between 100 and 100.1 might be small, most likely it will change significantly between 100 and 200, right? So these two, this might give us a somewhat accurate result, this will not give us an accurate result at all, but we can say 0.01 is somewhat small enough that the result will be accurate. So let's just take the function y is equal to root of x. This gives us dy by dx is equal to, this is x to the power half, so half x to the power minus half, 1 by 2 root x. That means dy by dx at x is equal to 100 is equal to root 100 would be 10, so is 1 by 20. Now we'll just write the equation y of 100.01 is equal to y of 100 plus, and here is the approximation we make, that between x is equal to 100 and x is equal to 100.01, dy by dx does not change much. It remains around 1 by 0.20. Oh, sorry, 1 by 20. So 1 by 20 times the change in x, which is 0.01, right? So 0.01 by 20 will be this term will be 0.001 divided by 2, or 0.005. So what we'll get the answer as y of 100 is 10, so 10.0005. And if you actually plug this value in the calculator, what you'll get is 10.000499.8, something like that. So we can see that our approximation actually is indeed quite close, because we assumed that between 100 and 100.1, dy by dx was a constant. Now just for a second, if we put this value, what is dy by dx at 100.1? That will be 1 by 2 root x, that will be 1 by 2 times 10.0004 4998, 2 times this, right? We can see that this number is very close to 1 by 20. So when we make the approximation that delta x is small, we are basically saying that these two numbers are quite equal, quite similar in value, and they are actually quite similar in value, right? They're very close together. The same thing would not happen if we took root 100 and root 200. So this was the first application of derivatives we saw. In the next video, we'll focus on the geometric perspective for derivatives, the derivative as the slope, and we'll see applications as they relate to tangents and normals. And after that, we'll see the final application of derivatives to find the maximum and minimum values of a function. Thank you.